So hello everyone. Thank you for being here today. And I'm going to present one of our work called Comfort-Aware Optimal Space Planning in Shared Workspace. So first, I would like to show you like a general overview of why we have a need for this work. So there is a plot shows the performance of the HVAC control strategy in terms of the energy consumption and the thermal comfort. We have the x-axis represents the annual energy consumption, and we have the y-axis represents the thermal discomfort ratio of the occupants, which is ranging from 0 to 1. And the ideal control strategy would exhibit a very low energy consumption and a low discomfort rate, which would be closer to the origin point. And currently, we have lots of different approaches to do that, to control the HVAC system. We have rule-based approach, which typically lies into the lower right section, as shown in the orange line, and it involves unnecessary cooling and heating to ensure the thermal comfort. And this approach tends to be energy inefficient because it consumes more energy to guarantee the thermal comfort. And in recent years, various data-driven and model-based control methods have been proposed. Some of those works have focused on identifying the trade-offs between the thermal discomfort and the energy consumption, which enabling the building manager to strike a balance between different objectives. But despite ongoing efforts by the researchers to improve this energy comfort trade-off curve on this plot showing on purple, there exists an infeasible area, which is the gray area, that cannot be surpassed for both objectives. Even with the assumption of the perfect building physical model, it is impossible to eliminate the thermal discomfort due to certain constraints, such as people have different thermal comfort requirements. So the presence of the gray area is mainly due to the fact that individuals have varying thermal preference in reality. So it is impossible to meet the thermal requirements of all occupants simultaneously with a single set points of each thermal zone. So to address this, one possible solution is to either we could provide each occupant with a personal comfort system. Basically, we could just let them to have a fan to cool down their own space, or they have a space heater to heat up their own space. However, it is costly. And in this study, we propose a fresh perspective by considering the controllability of the space allocation strategy. In other words, if we can reposition occupants within the building, we might be able to just basically surpass the lower limit of the thermal discomfort while simultaneously conserve the energy by using a better temperature set points. So in some cases, you might think that the relocation isn't feasible. However, many office buildings, especially in co-working spaces, are composed of shared workspaces that serve similar functions and can be booked independently. Co-working spaces, in particular, provide a variety of plans and pricing models to accommodate diverse requirements of their clients. Additionally, the conventional approach of space management in office building has experienced significant changes due to the impact of the pandemic. For example, some of the building right now, they offer hot desking and activity-based working environments. All of those employees can have the freedom to choose their own workspaces based on the activities they are involved in during the day, allowing for greater flexibility and adaptability in the workspace utilization. So here's a general overview of the entire work. In this work, we utilize a historical data to train some convex surrogate models. And these models correlate with the number of occupants and the temperature set points in each zone with the HVAC system energy consumption. We will then employ these convex surrogate models to solve some mixed integer programming problems, aiming to optimally assign long-term occupants. And this process reduces the energy consumption of the HVAC system and ensure the individual thermal preferences are met. The convex nature of these surrogate models significantly decrease the time that is required to solve this optimization problem. And additionally, we have developed two heuristic algorithms for online assignment of short-term occupants. And these heuristics utilize the surrogate models to predict energy consumption and make real-time decisions, achieving the performance comparable to the modified optimization problem in an online fashion. And by integrating for both long-term and short-term occupants assignments, we found that using just 2 weeks of the log data to train our convex surrogate models, it can lead to energy savings of up to 10%, where we don't change any of the existing control mechanism of the HVAC system. So in this presentation, I will explain the challenge in this work and how we formulate the problem as an optimization problem, and some techniques we use to tackle the problem, and finally, some experimental results. So while relocating occupants is a feasible solution nowadays, but developing an optimal assignment strategy remains a complex challenge. For example, here, in a 15-zone office building, there are over 500 billion possible ways to assign just 10 occupants. And additionally, determining the best temperature settings for each zone simultaneously with the occupant assignment adds another layer of complexity. And furthermore, it is crucial for occupants to know their assigned desk location in advance because they want to know that where they will sit and then just be more efficiently when entering the office, which rules out the possibility of learning an assignment strategy through trial and error methods. A practical approach to addressing this issue is to frame it as a mixed integer programming problem. In this formulation, the variables are the location of the occupants and the temperature set points for each zone. The objective is to minimize the building HVAC energy consumption. And to enhance the data efficiency in solving this problem, we're going to break down the building energy consumption estimation at the level of individual zones. This allows us for more granular and accurate assessment of energy usage and optimization opportunities. So this is the mixed integer nonlinear programming problem we identified. The objective is to just minimize the building HVAC energy consumption, which is the summation of the zone HVAC energy consumption. And the first constraint is the zone capacity, indicating that the total number of occupants assigned to any given zone does not exceed the maximum capacity. And the second constraint makes sure that each group of occupants is assigned to only one zone. Third constraint is the critical constraint that ensures the thermal comfort of each occupant is always maintained. And the last two constraints are just integer constraints and the acceptable range of the zone temperature set points that is defined in the HVAC system itself. So in this problem is NP hard, primarily due to the integer constraints. However, the branch and bound method can be used to solve it. If the problem is convex, then the branch and bound can solve it more efficiently, and the results can be near optimal. This implies that the zone HVAC energy consumption that we mentioned before, it must be approximated using a convex function. So to achieve this, we use an input convex neural networks. This particular type of the neural network is designed to ensure that the model output remains convex with respect to its inputs. So here is an explanation of how the SNN works, the input convex neural networks works. So basically, it has similar structure as the feed-forward neural networks. It has multiple hidden layers that you could use, and it maps from the input to the output. Additionally, we have these kind of the pass-through layers that link the input layer to each of those hidden layers. Because in order to make sure that our output is convex, we have to make sure that all of those weights that we learned in the feed-forward neural networks are non-negative. And also the activation function that we use are convex and non-decreasing. For example, in this case, we use a ReLU activation function. And because of those constraints that we included in these neural networks, we lose some of the representation capability of the neural networks itself. That's why we have these extra layers that basically link the input layers to all of those hidden layers in order to make sure that we can learn more information from the data that we provided. So here is a result of why we would need to use a convex function in our objective function. This figure shows a comparison of the execution time required by solving a MINLP problem using convex and non-convex surrogate models. Here we can see that the ICNNs use about 23 minutes to solve the problem to 0.01 gap between the upper and lower bound. And in the meantime, if we use a non-convex version, which is the random forest in our case, it takes about 192 minutes to solve the same problem to same optimality, because you can see the gap are are the same. They all the gap are all this at 0.01% level. So this is the most significant observation from this plot is that we use ICN as surrogate models can save about 80% of the time when we solve the MINLP problem, which help us to solve the problem more quickly without sacrificing the accuracy. And it's a crucial advantage in practical applications. And then that's what we do for the long-term occupants, which means that these people will present in the building every single day. But there is another type of the occupants that we also consider in this study, which is the short-term occupants. The short-term occupants are defined as the people who submit their desk requests on an ad hoc basis. Continuously modifying and solving the MINLP to find the optimal desk is not practical. And this approach is time-consuming and could impact the quality of service due to the delay in assigning tasks. So to address those, we propose to have some high-quality heuristic algorithms for on-demand desk assignments for short-term occupants. Here we introduce two different heuristics, the best fit energy and best fit space. The best fit energy algorithm aims to minimize the increase in energy consumption that results from accommodating the short-term occupants. This is done by first we sort all the zones based on the estimated energy consumption increase if they accommodate visitors to a given zone. And then we find the first zone that has enough space. And the dashed line here for the visitor groups. And then we find one of the zones that are not violating the thermal comfort of all the occupants in the zone after adjusting the temperature set points to accept the new visitors. In this case, we're going to pick the yellow zone as the results of this heuristic approach. And best fit space algorithm focus on a different thing, which maintains available space for the individual with different thermal preferences who may arrive in future. Here's a simplified version of the algorithm. We first draw a number of vacant space in each occupied zone on a temperature axis based on their current temperature set points. And then for the visitors request a space, we're going to assign them to an occupied zone that has the most available spots or a vacant zone if there's no occupied zone satisfy their temperature requirements. In that case, we maximize the possibilities of assigning more occupants in the future instead of just minimizing the energy consumption in the current time. So the complete workflow is presented as below. We first utilize the log data to train ICNN models for individual zones, enabling us to estimate the HVAC energy consumption within each zone. And then these surrogate models are used to allocate space to long-term occupants. Once the assignment is finalized, we're going to process the incoming requests from the short-term occupants through the implementation of heuristic algorithms. And we evaluate the hypothesis with three different baselines. The first two baselines are called the uniform algorithms, which distribute occupants evenly among different zones based on the number of available spaces and the ratio of the available spaces, disregarding the thermal comfort constraints in this case. And the third one is the random algorithm, where we randomly assign occupants to zones that meet the thermal comfort criteria. So this figure demonstrates the energy savings when the building is occupied by 100 long-term occupants. In this case, we only have long-term occupants in the building. The x-axis represents the total building energy consumption over 2 weeks, and the lower value being preferable. It is evident that the MINLP approach achieves the lowest energy consumption and thus outperforms the other methods. And this figure shows the performance of different algorithms for short-term occupants after we already have 100 long-term occupants assigned in this building using our proposed MINLP approach. On the left-hand side, you can see that all the algorithms are capable of maintaining the thermal comfort, because all of those at the beginning having a thermal comfort average thermal comfort probability higher than 0.8 in our case. We pick 0.8 as our threshold. But after that, we can see that the two baselines, the uniform number and the uniform ratio baselines, they have a very significant drop on the thermal comfort. This is because the uniform baseline assign occupants without considering their thermal preferences. They just want to put the people as much as possible in the building. And on the right-hand side, the figure shows the rejection ratio for different number of short-term occupants who submit their requests. Lower rejection rate means that we have more occupants in the building, which for the company means more profit. And the two proposed heuristic algorithms performs a little bit better than the random baseline and demonstrate a very similar performance in the case if we assign those short-term occupants by solving a modified IMA-NLP approach. In conclusion, it shows that the proposed heuristics offers a higher quality solution with significantly lower computational costs. And when these algorithms are used in the space management system of a co-working space, they will increase the profit by up to 17%. And here I will summarize 3 key takeaways from this presentation. The first one that space assignments can be done efficiently by using the input convex neural networks, which we see a 7 times faster solving time when compared to a non-convex surrogate models. And second key takeaways is that the heuristics are helpful because they can solve the problem with a similar result as the online optimization problem, which takes only 30 times less time compared to the case that if we solve it using optimization approach. And the third one that our algorithm can increase the profit of those co-working office buildings, and we can accept 100 more people with the similar level of the energy and also the thermal comfort levels. Basically, we are saying that those 100 occupants are the free money for the company to just assign them to the correct space. With that, I will conclude my talk and take any questions if you have.